Good afternoon. You had a chance to listen to the first part of my presentation in the morning in the plenary lecture. I will repeat something for those who are only on the workshop online very briefly, and then I will speak about the topics which I promised to address. So I will repeat that the uncertainty comes from several sources. For some sources, we need to know something about the physical nature of the experiment, and without it, we couldn't analyze it. It is the problem mainly of the systematic error or of type B error when we are not able to repeat the measurement of the same sample. So we must rely, for instance, on the calibration certificate. Just from repeating cannot find out whether we have or not a systematic error for this. We usually need mutual analysis of several quantities and perform so-called.
É workshop daqueles.
Sorry? Yes, please mute yourself at the computers so that we do not hear you here in the room. And there are only some components of uncertainty which can be analyzed by pure mathematics, and this is what I will talk about. So we will address only repeatability and reproducibility. Repeatability is concerned with repeated measurements under the same conditions, and reproducibility is analyzed mainly when we do critical evaluation. Dr. Kovanic, who invented mathematical gnostics, said that uncertainty reflects incomplete knowledge. So we do not have any assumptions what it should be like. And it's interesting to look, I think, at this paper by Andreas Pfennig, who showed that it depends whether a molecule is or is not present at the limit of the observable universe, and it changes the properties measured here in such a way that it looks randomly. So it's not necessary to have statistical random variable to describe uncertainty of measurements. So we have to remember that a value is not a number. So what we use in mathematical gnostics is based on mapping from real world to mathematics to the algebra of real numbers. I thought about it in the morning. And everything is based on so-called isomorphisms. So if we can describe the quantity or the phenomenon in one algebra, and we have another algebra which preserves the operation, and another which preserves the operation, then we can have, in principle, infinite number of such algebras, and all of them are equivalent. And if we know this mapping and this mapping, we can derive mapping from this algebra to this algebra. And the importance is that we can do some operations in one algebra and not in the other. So, for instance, we don't know how to do this operation, but we know how to do this, and we know the mapping. So we go from this algebra to this. We do the operation, and we return back to the original algebra. So this is the most important part from mathematics. So we can have additive and multiplicative model. They are equivalent. The reason is that this is better for the case where the measurement error does not depend on the measured value. This is better in case that the error is directly proportional to the measured value. It's of course equivalent, and later in the lecture you will see that sometimes I use A, sometimes Z, so do not be worried, it's equivalent. And then we can use metric model, we can use, I noticed in the morning that there is an error, it should be pair numbers, and we have two types of pair numbers, complex numbers with imaginary unit the square is equal to -1, and double numbers where it is equal to +1. The complex numbers are model of Euclidean geometry, and the double numbers are model of the Minkowskian geometry, so that the model of uncertainty is isomorphous with distance and rotation in Minkowskian geometry. It's used in Lorentz transformation in the special theory of relativity, and we can go to the Boltzmann equation for entropy, and knowing it, and remembering statistical thermodynamics, we can go from entropy to probability. I will just mention briefly that we have four types of distribution functions. They can be estimating, which are not sensitive to outliers. So if I add an outlier to a set of data, it will not affect the result. And quantifying, I will not talk more about it. And we have local and global, where local can describe multimodal distributions, and global does not exist for all data because it assumes that the data set is homogeneous, and we find that the best fit is not a distribution function. It means that the sample is not homogeneous, and we do not need some pre-selected probability. We have a simple yes/no answer whether it is or it is not homogeneous. I showed briefly in the morning the example from the database. Such problems can be found in all big databases, so I do not want to say that NIST doesn't do a good job. And you see that NIST presents this value with such a large uncertainty, so it's unusable. And if I analyze the same 12 literature values by mathematical gnostics, I get this results. Well, it's a bit more optimistic because I analyze only repeatability. I do not take into account the properties of the mercury thermometers which were used, so the combined uncertainty should be higher than what I found just by pure mathematics. If I look at it, this is the estimating local distribution function, and you see the steps on the probability and on the G line with the lower scale parameter for peaks on the distribution density. So it is a signal that the values do not represent one quantity. This is the estimating global distribution function. I intentionally let the software to find the limits of the axis. So when it needs negative values for the distribution density, it means that the distribution density is negative. So I made a detail of this part. You clearly see that the distribution function has a decreasing part, and you know from statistics that distribution function must be non-decreasing, and you know that distribution density must be non-negative, and you really see negative parts, which means that the best fit is not a distribution function, and in other words, the sample is not homogeneous. So if we remove the outliers, which are detected by positions of the local minima, we get such a distribution of the homogeneous subsample. You see that it is slightly asymmetric, so it looks like normal distribution. It's similar, but it is not normal distribution. And when we have a homogeneous subsample, we have local estimate of location. Estimate of location is the term used in statistics. And here we use it as the maximum of the distribution density, which, as you know from statistics, is the most probable value. And if we take this sample and add a value which is larger than the estimate of location, it is shifted to higher value, but only up to this point. And if the added value is larger, it goes back and asymptotically reaches the same value. So this is because it is automatically considered as outlier. It gets a lower weight and that doesn't affect the results. So again, we have the simple yes/no answer. If we want to test whether another value is in agreement with the data, whether it is in the tolerance interval or not, or whether it is in the interval of typical data or not. And as you can see at the values, the tolerance interval is always a subinterval of interval of tolerance data. This is just an artificial example, so it's symmetric, but in reality, it's quite often asymmetric and can be very asymmetric. So we can split the data to these classes, starting from outliers to subtypical, typical, tolerated, and symmetrical to the higher values. I don't know how much time I still have. Okay, so this is this is the tolerance interval. So this is the interval where the characteristic value should appear and can never be shifted out of this. This is interval of typical data. So the measured value will typically appear here. The subtypical and overtypical have a bit higher error, but still not outliers. And these are outliers, so if we add them, we will not have homogeneous sample. So this is the result. So you see this is a tolerance interval. This is the interval of typical data, and these are the limits after which the value is considered an outlier. So you see that even this interval is narrower than plus minus 80 from NIST. So if we look at those 12 data, we found that these three are in the tolerance interval. This is in the interval of typical data, and this is subtypical. These are overtypical, but still not outliers. And we these values which were detected as outliers. If you know thermodynamics, then even without looking at the sources, you can find that these are boiling temperatures measured at reduced pressure, and you cannot recognize why these are outliers. You have to look at the sources. You find that they are taken from the catalogs, so probably these are boiling temperatures of a technical solvent, not of a pure compound. And we can imagine that it's not easy to remove non-volatile impurities. And if you have a liquid with non-volatile impurities, it will increase the boiling temperature. And I want to say that precision and correctness is not the same thing. Fortunately, I know the authors of this paper. It was measured in our lab before I entered it, and so I know that they do the measurement very carefully. And it was part of the measurement of vapor-liquid equilibria, and the student who entered the database, the value to the database, was instructed that if he sees vapor-liquid equilibria, that at mole fraction 0 and 1 are the properties of the pure components, and if it is vapor pressure, so it's the same as boiling temperature. It depends from which side you look at it. But he was not careful enough. So this value is precise with respect to repeatability. I'm sure that they repeated the measurement and it was repeatable. I'm sure that it is correct because I know how they did calibrations of all instruments. So if they say that they measured, well, it was a thermal measurement. So they measured pressure at this temperature. Everything was calibrated. So it is correct as a boiling temperature at the pressure which is given in the paper, but it is not correct as normal boiling temperature because it was a reduced pressure. So it was mainly important message for students that precision and correctness is not the same. And now I switch from one-dimensional data to regression because we do not always measure properties at one condition. We are usually interested at some dependence on temperature, on composition, on pressure, on voltage, on whatever. And in such a case, because we need a lot of measurements, we do not repeat the same measurement many times at the same conditions and then at other conditions. So we want to analyze the uncertainty using regression. And because we can have data with higher error from time to time, then we need robust regression. It's known even in statistics, and statisticians use regression along an influence function. The trick is that we set a posteriori robustifying weights usually to be all equal to 1. Then we optimize the model by a normal weighted least square method. Then we evaluate the residuals. These are the differences between calculated and experimental values. And then we use influence function and recalculate the robustifying weights. And go back to point 2 and repeat the procedure as long as until we get almost the same residuals from subsequent iterations. And the difference is that statistics has a few dozens different influence functions, each derived from different properties. And if you want to prove that the outliers have that properties, then you cannot do it by statistical means, because if you want to test whether the errors match preselected distribution function, you need 50, sometimes even 300 repeated measurements, depending on the type of distribution function. But everybody tries to measure without large errors. So you never have so many measurements with large errors so that you can prove that you use the right influence function. And the influence function can fail unpredictably, but because mathematical gnostics has generally one assumption that the value was measured, then it need not be the best method if you know exactly what is the model of your gross errors. You can use the influence function for this model, but I haven't found any case that the gnostic influence function would fail. This is one of our results. It's measurement of temperature dependence of dynamic viscosity of 3 different ionic liquids. And you have 2 columns. The first is residual, so it's the difference between the calculated and experimental value. And the second is the gnostic weight, which is the result of the regression. And if it is close to 1, it means that it is that the value is in a good agreement with the fit. And if it is low or even close to 0, then the agreement is poor. And you will find that we almost always have the values very close to 1, and only at this temperature for all liquids, the robustifying weight is almost 0. So I got the data a few months after they were measured. So it was not possible. It was measured in France, and I analyzed them in Prague. So it was not possible to go back to France and look at the instrument, what happened. The girl who did the measurement just noticed that at this temperature, and only at this temperature, she many times got error message ball not found. So it was some strange problem with the instrument at this temperature, and only at this temperature. I cannot say why, but I was able to detect that it's not wrong. But anyway, the fit is so good that if you look at the graphs, you will not recognize that something was wrong. And now I will talk about the data which Errol used on his lecture on June last year. These are the literature references from which he took the data. And just to repeat, no matter whether I use statistical or agnostic regression, there is one common requirement that the model is correct. If it is not correct, that we can be sure that we will get incorrect results. So we can use a polynomial almost always because it's based theoretically on Taylor series expansion, and we almost always can afford it, or we can have equations derived from theory. But in the case of Taylor series, if the dependence is quite complex, we may need too many parameters, but we do not have so many data. So we have to cut it. So we have an approximate equation. And similarly, if we use some equation derived from theory, it always has some simplifications. So again, it's not fully correct. And it depends whether the incorrectness made by the simplification is much lower than the experimental errors, then we can use it. Or if it is comparable to the error, then we will have the problem. So this is what GEP box said, all models are wrong, but some of them are useful. So we always use wrong models which are useful. So I used these 5 models. I didn't know all of them at the beginning of my work. I just summarized all of them here, and then I will follow the procedure as I did it. So first I plotted the data, and I found that if I plot logarithm of x, again temperature, it's almost linear. So if you look here, it looks quite well. It's here somewhere in the middle. So if you look at this graph, you can be satisfied. But you should not be satisfied if you do not plot the residuals. And if you do it, you see that you have several clear trends. You have one trend here, another trend here, another trend here, another trend here. So it means that, well, it looks nice, but it's not a correct regression. So, okay, if we try to go to the quadratic polynomial, then you see now it's selected these points as better, but still in the residuals, there are the same trends. So going from linear to quadratic doesn't help. And it seems that I would have to go to a very high order polynomial. So this probably is not the right way to continue. So I tried x instead of logarithm of x, and I went up to the cubic polynomial. And what you can see that now we have this cluster which is randomly scattered around 0. The deviations are quite low, and then we have some clusters which do not agree with these data. So this is the data by Song and Law et al. Number 3. And then I used the same equations which were used by Errol in his presentation. So this is the model with 2 parameters. Again, you see that it is quite good regression, and you see the main cluster which is composed of the same data. And here I tried the same with 3 parameters. If I switch quickly between this, you see it doesn't change. It doesn't change here, and you can see the differences in the residuals. So I wanted to know whether there is really a significant difference between these two equations. So the left plot shows the difference between these two equations. And for comparison, these are the residuals. So if you look at the numbers, so the difference between the equations is somewhere here. So there is almost no difference in the middle of the graph, and I have the residuals here. You can see the difference between the models here and here, and then at this end, but not in the middle. So it doesn't matter much whether you use only 2 parameters or 3 parameters. And now, this is always problem in publications that someone does some regression, calculates the uncertainties in parameters, and the parameters are rounded, and the reviewers say you provide too many decimal digits, you have to round them. So let's look what happens if I round the parameters. So I took this equation. I use only the data by song and law number 3, and I get these parameters as the precise values. And I say, okay, 3 digits might be enough, so I round them like that. So I make the plots. So if you compare here the difference between the precise and rounded parameters, you see, okay, it's perfect. This is again the difference between the precise and rounded parameters. It's not very high. But now I will show the residuals. This is for the precise parameters, so you see it's randomly scattered around 0. So this is good result. But now you see we still have some good scatter without a trend. But with the exception of this one, all residuals are negative. So it shows that it is a bad regression. So how to find the required precision of parameters? So we have a dependent variable, which is a function of n independent variables and p parameters. If we want to study the effect, so we express the total differential. The first sum is the effect of independent variables, and the second sum is the effect of parameters. And well, we want to know how many decimal digits in parameters we need. So for this case, all these dxy will be 0, so this sum disappears. Then we can replace differentials with differences and use error propagation law. So we get this equation, and we will naturally wish that each of these term contributes equally. So this is the minimum difference in the independent variable which you want to distinguish from 0. This is the maximum of the absolute value of the derivative with respect to the parameter, and this is the maximum rounding error which we can afford. So if I go back to this equation, we saw that the residuals were within this range, so we should be able to see errors up to 0.001. If we do the derivatives with respect to parameters and find the maximum, then for A, it is 1, it's constant. For B, it's a reciprocal temperature, and the highest value is for the lowest temperature in the range, so 1/290. And for C, it's a logarithm of the highest temperature in the range. And we substitute it into the equation from the previous slide. We get these maximum errors in the parameters which we can afford. So if we compare it with a precise value and with a rounded value, so if we want to have good fit, we must not round them. So we really need these parameters. And I did the same analysis just for the cubic polynomial, and because here the cubic term I have 360 to 3 to have power, so it will be very large number. So in the parameter, I really need all these numbers. And what I see in the literature, that sometimes they have polynomial in temperature in degrees centigrade from 0 to 30. So from 0, the precision is determined just by the intercept, but for the other end on the interval, it takes into consideration to the rounding errors of.
Ô, Neidinha, olha o que ela fez.
Of all parameters, so you really need a lot of digits. And I promise to explain why statistics sometimes works. So this is expression from the additive model. So this is the difference between the calculated and experimental value. And we have these expressions. So if you look a little at the expressions, you can find hyperbolic functions in these equations. And H is relevance. It models the error. And it is bounded. So if the deviation goes to plus or minus, deviation is bounded by -1 or +1. So that's why gnostic is robust and not sensitive to outliers. Similarly, gnostic weight plays the same role as statistical weight, and it's 0 for very large deviation. So this is the second reason why it is not sensitive to outliers. And we can do Taylor series expansion of these properties. So for very small errors, we stop at the linear term. In small errors at the quadratic term. And in gnostics, we either want to minimize the sum of squares of irrelevances or maximize sum of squares, sum of data weights, or find the extremal values of entropy and information. And if you look here, so if we have small errors and we can afford Taylor series limited to the quadratic term, then it is equivalent to least squares method. So that's why statistics works for small errors, even if the errors do not have normal distribution. And you know, if the value is measured, is disturbed by entropy, so the entropy rises and we lose information. And then when we want to analyze it, we need to decrease the entropy and we obtain the information. So for small errors, it's compensated, and for a large error, in extreme case, the entropy fall is -1. So we have to decrease entropy by 1. But we get information which is equal only to natural logarithm of 2. So it means that it is impossible to get back all information which was disturbed by entropy, and we can formulate it similarly as in thermodynamics, that it is impossible to construct a machine which would produce at least as much information as would enter into it. So we cannot create information perpetuum mobile. So that's all from me. Yes.
Time for questions. Oh,
It's fine.
Thank you, Zdeněk. I think I finally begin to understand. And that's something I've wanted for a long time. I had 2 or 3 questions. One, towards the end, you had an equation for the standard uncertainty. It looked like the Gauss equation, but it was written in terms of the standard deviation rather than in terms of the variance.
I don't know which one you mean.
You had u of y equals the sum of the differentials times the variable, and then what I presume, or maybe you had 2 terms of that type. I mean, what I'm used to seeing is u squared is the sum of terms of the type differential squared times u of the variable squared, and then a second term in the covariance of the.
I don't understand what you.
Go back. We can talk about it later. If it looked like the Gauss equation, but wasn't the Gauss equation.
Yes. I talk more about the theory in the morning. So the aggregation in statistics comes from isomorphism with classical Newton mechanics, and the gnostic aggregation from the isomorphism with relativistic mechanics. So the equations are sometimes quite similar, but they
Okay.
use different quantities.
Okay, I was expecting it
And-
to be one thing and it was
and
something
then-
else.
Anyway, the result of mathematical gnostics is a distribution function, and it must have the same properties as statistical distribution function. Otherwise, they will not be usable.
okay. Maybe I can have a contribution to complete one of the tables that you showed. And if you don't mind, I will share my screen because it's not going to work. I don't have the right to do this. Okay, because I wanted to show the figure of the viscosity, which you showed
Yes,
the data. You showed the table, but the plot actually, if you have a look at it, and I'll gladly distribute the paper to all of us, you don't see it from the figure. the
the-
figure is, you know, the fit is perfect.
Yeah,
When you look at the data, I
the-
wouldn't say there was a problem,
Yeah,
so.
the value is, the error is larger, but still comparable to experimental errors. So you cannot find it without gnostic analysis.
Okay, so we have a question from the chat. Vladimir Diki is asking, are there any code implementations of the method which can be used by the community?
There is one implementation in Octave, and it's not very user-friendly, and user-friendly version is in preparation. It was my plan to have it ready before this conference, but I had serious health problems, so I didn't manage to complete it, but I think I need just a few months to finish and to present something.
Okay, any more questions? Oh, the two. So, yeah.
Okay.
Okay.
Okay, so my question is about the robustifying way to thought about further regression. So how do you calculate that, like for dummies? 'Cause didn't understand. And how can you use that, or what is their importance when doing the regression?
Yes, I will go to the slide. So here the procedure is quite simple, because the most difficult part is just simple statistical regression. But if you have some values which are subject to gross errors, then the result of the regression will be influenced mostly by the worst data. And then after this step, you evaluate the residuals, you put them into some function, it's called influence function, and it will calculate the statistical weights, or well, it will calculate the weights which should be used in the next regression. And it depends which influence function you use. There are a lot of functions in statistics, and the gnostics comes from this equation, which calculates the information which is contained in the data. So if there is good information in the data, it will increase the data weight. If it's low information in the data, then the weight will be lower. And because after the first step, the regression can be very bad. So it's not sufficiently sensitive after the first iteration. But in the second derivation, it gets closer to the good values. And after a few iterations, you can very easily distinguish the good values from outliers. Usually you need about 5-6 iterations. In the most difficult case, it's 30-35 iterations, but they are really fast because, well, you just repeat and you get the result within a fraction of a second. So it's not a problem with nowadays computers.
Okay, there's a question from the met.
If I have time, Maybe it's my fault that I didn't understand well. I'm referring to the part in which you talk about the number of digits that you have to consider, the very last part of your talk. Of course, everybody agrees, I absolutely agree with you that sometimes, and you have, of course, the statistical instrument to decide how many digits we should use. But I'm referring, for example, to the fitting in the end of experimental data, because the uncertainty on the adjusted parameters sometimes should, at least in theory, and I want to know your perspective, what is the uncertainty on the data that we are going to fit? So sometimes we have an uncertainty on the adjusted A, B, or C parameter to the second digit that, of course, it's not good to fit perfectly our data, but comes from data with other uncertainties. I don't know if I have been clear. So you have a lower modeling power, that's true.
This is
but-
another problem. I haven't talked about it because sometimes the parameters have some physical meaning.
Yeah.
You want to use them in another calculation, and then you are not interested in the precision of fitting, but also how large error you introduce into your subsequent calculation. And for this, you do not need to know just uncertainty of the parameters, but also
Yeah.
covariance, because the parameters are often correlated. So,
Yeah.
well, I have no,
I
not
agree.
enough time to talk about everything.
Yeah. The same occurs when,
Yeah.
and then I stop. We find very often in literature, let's say overfitting, especially with polynomial functions for something in which they increase the number of parameters to adjust, and then you have a better fit, but the real meaning of
Give me enough parameters and I can describe an elephant. Yeah.
exactly with a polynomial function of 5. Yeah. This is something that we all should take into account when we review papers.
Okay, we have a question from Alla Bazilova, who's online. So Alla.
Thank you, Zdeněk, for your presentation. Can you hear me?
Yeah.
Okay, so first of all, about your first part about boiling points of 1,4 dichlorobutane. So it's, I would say can you hear me? Or there's something?
Go on, please.
Okay, so first of all, so the NIST web book, it's just a collection of data. It doesn't analyze the quality of data and the origin. So it provides the origin, but it doesn't analyze the quality. So that's why the average values they shouldn't be considered as recommendations from NIST. So they just done a simple average. So that is one point. The second point is if you are looking for a more reliable assessment of data, so from NIST, so it's better to look into Thermodata Engine or WTT resources where there is a more detailed analysis, including multi-property consistencies, for example, vapor pressure. So normal boiling point, it's a part of vapor pressure data. So that's why it involves the analysis of temperature dependence of vapor pressure, involving the consistency with heat capacity of liquid, of gas, densities. And I just look into TDE, and the value which was obtained based on this analysis is 428.3. So it's very close to what you recommended. So but it involves more pressure points involving lower pressure point data. So just to let you know that web book is not a resource for looking into NIST recommendations. And also okay, so that is it for I don't want to take much of your time.
My fault was not meant as criticism of NIST. I told in the discussion in the morning that I saw such problematic data in atomic databases. For instance, it was a normal boiling point temperature listed as a critical temperature. So I know it happens, and I just wanted to show that it could be detected automatically by a simple procedure. So I know how it happens in big databases, so do not take it critically. I understand it.
No, I'm not taking it critically. I'm just saying for everyone that webbook is not the resource for recommended NIST data. Just to inform everyone that it shouldn't be considered as a resource of recommended data.
Okay.
Okay. So thank you very much, dear Zdeněk, for your very nice and interesting